video on thermal physics. Let's take a look at this question. A metal cube of mass 75 grams is heated in a naked flame until it is red hot. The metal block is quickly transferred to 200 grams of cold water. The water is well stirred. The graph shows the variations of the temperature of the water recorded by a data logger during the experiment. So what we're doing is heating a metal cube in a flame until it is red hot. So we know that's going to be extremely high temperature. Then we're putting it into some cold water and we're giving it a stir, and there's a data logger, a computer that's going to record the changes in temperature of the water as it cools the metal block. Let's read the last part there. The metal has a specific heat capacity of 500 joule kilograms to the -1 Kelvin to the -1. Use the additional information provided in the graph to determine the initial temperature of the metal cube. You may assume there are no losses to the environment and all heat transfer takes place between the metal block and the water. Okay, so let's start as always by writing down what we know. Okay, so straight away, metal cube. So we know the mass of the metal cube, so I'm just going to put mass of cube equals 75 grams, which is 0.075 kilograms. Heated in a naked flame, metal block is transferred, mass of water, mass of cold water, CW, cold water, equals 0.200 kilograms. What else do we know? We've got the graph there, and then it says specific heat capacity of the cube, of the metal. So C of C, specific heat capacity, equals 500 joule kilograms. 500 joule kilograms to the -1 Kelvin to the -1. Use the additional information provided in the graph to determine the initial temperature of the metal cube. You may assume there are no losses to the environment and all heat transfer takes place between the metal block and the water. What we know is that energy lost, or energy transferred, energy lost by the cube is equal to energy gained by the water. So we can write that MC, mass of cube, C of C, delta T, change in temperature, equals mass of water, C of water, delta T of the water. Okay, and if we plug the numbers in, so this is going to be M of C, which is 0.075 kilograms. I won't write the units because they're very lengthy, times by C, which is 500, and then we want initial temperature minus final temperature initial, we don't know yet, equals minus temperature final, which is, if we look at the graph, is 48 degrees C is the final temperature of the water, and when the temperature and when the block has stopped transferring energy to the water, that means the water and the block are at the same temperature. So the final temperature of the block is also 480 degrees C. We can use degrees C, that just means we're going to get our answer in degrees C. So provided that all of the delta T's are in degrees C, that's okay. We can use Kelvin or we can use degrees C. In this case, we're just going to keep it in degrees C. Okay, and that is equal to the mass of the water, mass of the cold water, which is 0.200. I don't need to write that, we could have written 0.2, times by, and this is the trick, this is assumed knowledge that we know the specific heat capacity of water. Luckily we do, 4,200 joule kilograms to the -1 Kelvin to the -1. That is the specific heat capacity of water, which is assumed knowledge. And then we have, in the case of the water, we've got final temperature, 48 degrees C, minus initial temperature, which we can see on the graph is 18 degrees C. bit squashed at the end, but I think you can just about read that. Okay, and then we just got to solve this out. Okay, so let's start here with this part. 0.075, 0.75 times by 500, 37.5. And we can expand out the brackets, so that's going to be times by ti, and it's going to be minus 37 times 48, 37.5 times, should have started over there really, shouldn't I? 37.5 times 48. That's just expanding out the brackets. And that's equal to, on this side, 0.2 times by 4200, 840, and then this we can see is just 30 degrees, so 840 times by 30 degrees. Okay, and then we want to know temperature initial, so what do we do here? Let's first just calculate that bit out. 37.5 times 48, 37.5 times 48, 1800, and if we add 1800 over here, then that's okay. So 840 times by 30 plus 1800, and that gets rid of that on this side, and then we just want to divide by 37.5. Okay, and that leaves us with Ti on this side, so just divide by 37.5, and that leaves us with what we want to know, temperature initial of the block. Oh, so let's just work that out. So 840 times by 30, 840 times by 30 plus 1800 divided by 37.5. I think that would, I don't know if that's going to work. Maybe we need to equals there, and then just to make sure, 37.5, 720. And that is in degrees C. We could have done that in Kelvin, it would have given us the same answer, and our answer would have been Kelvin. If we want to convert that to Kelvin, we're just going to have to minus 273 degrees C. No, we're not. What are we going to have to do? If we want that in Kelvin, we've got to plus 273 degrees C. Go. Plus 273. And that gives us our answer in Kelvin.